Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session on PLL building blocks. So, after looking at the loop gain, phase margin and noise analysis in PLLs at system level, what we will do is we will now move on to the block level design for PLLs. Okay. The first one, which is the most important block in PLL is the oscillator. Okay. So, let us look at what is this block and how does it work, how we are going to design it. So, we have used repeatedly a block named VCO, voltage controlled oscillator, where we control VC and we get V out whose frequency we can control. So, just to add details to this block connects to the supply VDD and ground, and you do not feed any other signal other than the VC signal, and VC controls only the frequency. It does not control the amplitude of the oscillator. Okay. So, you have this V out. So, you can think about it, this particular block operates stand alone. It takes power from your VDD and converts that to one particular frequency. Okay. One particular frequency, whatever frequency you have V out, it can be A times sine of omega in omega naught t, or either it can be a sine wave or it can be a square wave of the same time period. It depends on the kind of oscillator which you have. Okay. So, this is the time period of the oscillator and this time period t is equal to 2 pi by omega naught. So, the oscillator as a standalone block, it generates frequencies depending on the control voltage. Somehow this control voltage will relate to your omega naught, okay, but there is no other input to the oscillator. There is nothing like sinusoidal input because of which you are generating omega out. No, it does not happen like that. Okay. So, this block we need to design this block actually, and there are multiple options before you for this block which can generate sinusoidal output. So, let us look at the options which are available to substitute your VCO. The first one is crystal oscillator. This is the part which we saw in the very beginning of this course. Okay. So, crystal oscillator, it operates on the piezoelectric phenomenon, okay, and the characteristics of this crystal oscillator are as follows. It is generally a low frequency output at you get. Okay. The frequencies are low, it may be ranging from few kilohertz to few hundred megahertz at the max. Okay. So, the output is low frequency, the frequency stability is excellent. So, what is frequency stability? I will just tell you, frequency stability is excellent here, which is so when you have a crystal oscillator whose output is at frequency f naught, right. F naught is a function of your device sizes within the crystal oscillator, and this frequency f naught may vary depending on the temperature, depending on the voltages which we are feeding to the crystal oscillator and other process parameters. So, that variation in for the frequency, we are not applying any force, any sinusoidal inputs to the system. This is the oscillator standalone, it has its frequency output at FO, but FO can vary. So, whatever the variation you have in the output frequency by the nominal frequency, or you can say the average frequency, into 10 power 6 is measured as parts per million. This is the frequency error. Okay. So, the frequency error in crystal oscillator is very low, and that is why we say that the frequency stability is excellent. This is typically in the range of 10 to 100 ppm. Typically, it depends on what kind of crystal you are choosing. Okay. Then the other important metric for the oscillator is your phase noise. So, crystal oscillator comes with excellent phase noise. And what is this phase noise? Well, it means that if you use the oscillator stand alone as a clock, the jitter is going to be very low, or the phase noise is very less. So, if you look at the spectrum of the crystal oscillator, you may get a tone, okay, and then very low phase noise is like the perturbations near the output frequency is going to be quite low. Okay. That is what you are going to have. Whereas, in other oscillators you may get a lot of phase noise. So, this is your crystal oscillator output spectrum. The bad part, the only bad part about the crystal oscillator is they are quite bulky. Okay. So, crystal oscillators are bulky. Okay. You cannot integrate these crystal oscillators with your integrated circuits because they are too big, right. So, you cannot integrate on your IC, and having multiple crystal oscillators even on the PCB board will be too much because they occupy a good amount of area. So, this is the drawback, not the only drawback of the crystal oscillators. This is one drawback, and this is the another drawback for the crystal oscillator. The good part is your frequency stability, your phase noise. So, in case you need low frequency output and you need a low frequency clock and you are not integrating on chip, you are integrating on board, you need only one part of one oscillators, you may be good enough to use the crystal oscillator in place of using any PL, but that is the limit. Okay. As we move ahead and start realizing the oscillator using tuned oscillators, which are tuned LC oscillators. Okay. This is something which we saw when we told that okay, the electrical model of the crystal oscillator can be realized using RLC components. From there, we found that the frequency was limited by L and C, inductor and capacitor values. So, we can go and choose the inductor and capacitor values as we want, and we can realize that. So, here the frequency is not the limit, you can very well get not low frequency will have its own problems because inductors may be very large, but you can get in general low to high frequency outputs. Okay. Frequency is not an issue, provided you are ready to sacrifice the area for the inductors, but that area is not as large as the area for the crystal oscillator unless you go to a very low frequency. The other thing is frequency stability is not excellent, I would say, but frequency stability is good. So, it is going to vary, there is no doubt about it. So, your F error will actually be large. Okay. It can vary from 100 ppm or depends on the values, it can vary up to 1000 ppm in general. Okay. The next one is your phase noise. Phase noise is good, but not as good as your crystal oscillator. So, phase noise may increase. Just for an example, I may have a larger phase noise like this in comparison to your crystal oscillators. Okay. Then when we come to the point of integration, they can be integrated, can be integrated on chip at the cost of large large area for inductors. Okay. So, as you go to the lower technology nodes where the chip area, price per unit area is quite large, integrating these inductors may not be an option always. Okay. So, inductors are initially the inductors were kept outside the IC because they were huge. As the silicon got cheaper, we have started integrating the inductors on chip also. So, it completely depends on the value of the inductor which you are having, whether you will integrate on chip or put it on board. Okay. So, the examples of tuned LC oscillators are your Colpitt's oscillator. Okay. Colpitt's oscillator, Clap oscillator, Hartley oscillator, right. Okay. Another one bad part about this I would say is that you have the frequency tuning is limited. Frequency tuning range is limited. In case of your crystal oscillators, frequency tuning range actually does not exist. So, once you design a crystal oscillator, the frequency, whatever the frequency you have, that is what you get. Okay. Frequency tuning range is roughly absent. Okay. So, you have to design it carefully for the desired frequency. Here the frequency tuning range is limited, and the reason is that the frequency at which it is oscillating is roughly equal to or is equal to 1 over L and C. So, how much capacity you can vary, okay, it will depend on that, and there will be limitations on that also. You cannot vary inductor that easily for an LC oscillator. Okay. As you see, in comparison to your crystal oscillators, the good part about this is that it can be integrated on chip. You get a wide range of frequencies during the design process. So, this is low to high frequency output is during the design process. Once you have designed the oscillator, okay, you cannot tune that frequency. That is the frequency tuning is very limited. So, these are the good parts about your tuned LC oscillators. The bad part with respect to your crystal oscillators is these two things are not that great. Okay. Now, the other one, because we are looking for the things where in our PLL we can vary the output frequency, we want good stability also in those things. So, there exists another kind of oscillators, and this is ring oscillators. Okay. So, in ring oscillators you can say a large tuning range, even after you can have a large tuning range during the design process, and once it is designed, by controlling few things you can have large output tuning range. So, this is like a good part of it. Frequency stability is poor. Frequency stability is poor, which is like you cannot use the ring oscillator stand alone without keeping it in the phase lock loop, because the frequency will vary depending on process, voltage and temperature. Okay. So, frequency stability is poor, phase noise is also poor. So, lot of phase noise. So, if you are looking at this, standalone oscillators may show you a lot of, ring oscillators may have a lot of phase noise. Okay. You can easily integrate it on chip. Okay. Integration on chip is not at all a problem. they occupy a very small area. Easily integrated on chip occupies a small area. So, if you want multiple ring oscillators on chip, you can easily integrate them. Okay. So, if we think about it, large tuning range is a good part, frequency stability is poor, this is not good. So, you cannot use standalone, phase noise is poor, again you have to use in a PLL loop, easily integrated on chip and occupies a small area, that is good part about the ring oscillator. So, these are 3 different kinds of oscillators. We will talk about the last 2, and because in many places we need oscillators with a wide tuning range. Okay. So, we will start with the ring oscillators to begin with, right. So, let us come to this block, which is VCO. So, I will just draw this and just give a thought to it, what should it do. So, you have VDD and ground, forget that you are controlling VC, just assume that VC is equal to some fixed voltage. Okay. So, VC is fixed, for example, okay. And you are getting V out here, and in practice what you want to see is this V out should be sine wave and it is self sustained. So, think about a system where you are not feeding any input, all the voltages are DC and it is producing sustained sinusoidal or square waves at the output, which means that the system, whatever system we are using, that system should be self sustainable, okay, which in turn means that even if there is some disturbance at the output of V out, the system takes care of it and it still retains the frequency which it is designed for. So, to understand those systems which is self sustainable even in the presence of disturbances, we have to understand closed loop feedback systems. Okay. Closed loop feedback system. Okay. So, I was like it is a closed loop system because I use the word closed loop because if you make any disturbance it takes care of it. So, in general let us draw a block diagram of a typical closed loop feedback system. You have a forward path with gain h of s and you have a feedback path or gain a of s and you have a feedback path with gain beta of s. This is the system, and if it is in negative feedback, then I can put a minus sign here. Typically in closed loop system, this is your V in and this is your V out. Okay. So, this system will become self sustainable, okay, without any input under given conditions. Okay. So, what is that? So, the loop, first we look at the loop gain of this system. Loop gain is the gain which you get as you break the loop and go around the loop. Okay. So, here the loop gain is equal to A of s times beta of s. We have to keep in our mind that there is a negative sign in the feedback. This is important. Okay. So, now given this loop gain of the system becomes self sustainable above system is self sustainable at, because we are writing in Laplace domain. So, we will talk about frequencies at frequency omega equal to omega naught if magnitude of loop gain at j omega naught is equal to 1 and angle of loop gain at j omega naught is equal to 180 degree. If this happens, then you will have sustained oscillations at the output of the system at omega naught without any external input to the system. So, you can think that this is like a small signal model of a closed loop system, and that is what is going to replace your oscillator. So, let us understand why these two conditions are important. By the way, these two conditions for sustained oscillations are defined under Barkhausen criterion. Okay. Okay, this is condition for sustained oscillations. So, let us take this example and try to understand that. So, just to begin with, think about it that you in the beginning you feed in a sine wave like this, only this sine wave. Okay, with respect to time, it has time period t and t is equal to 2 pi by omega naught. This is what you feed in. Okay. We will see that how we can think about that this kind of frequency will come on its own, but this is the sine wave you feed. So, initially all the voltages were 0. So, V out was 0, feedback was 0, everything was 0 and I feed this input. When I feed this input here, so the input comes here, it will get amplified by the gain A of t and it will come here. Okay. A of t is going to add some kind of gain to it. So, in place of just having the same blue waveform, I am actually providing some phase shift and some amplification. Okay, that is what I am going to have at one particular frequency. So, at one particular frequency, there is going to be an amplification and phase shift. Okay. So, that will happen at output A of s. Then what happens? You have beta of s also, and beta of s is going to do the similar thing. It will amplify and it will actually amplify and add phase shift to it. So, the waveform here is shifted in phase and amplified. I deliberately do it like this. The reason is the following. Okay, so let me do it with the same amplitude and okay. So, here what I am trying to make sure is that this amplitude, if this is amplitude small a, then this amplitude is also small a. Here it is 0 and then you see positive cycle first, here you are seeing negative cycle first. So, effectively what I am trying to show you here is that this signal is just an inverted signal which you fed at the input, which in turn is just telling you the same thing, that if I feed this sine wave V in, then from V in, when I multiply my A of j omega naught times beta of j omega naught, I effectively what I get is minus V in. That is what I am doing. If I get that minus V in and you have a negative sign sitting here, so what happens is this negative will invert this signal and you are going to get the same signal here. Okay. So, now you think that you provided the sine wave to begin with as per our understanding, and then the system itself is also feeding the sine wave. If the system itself is also feeding the sine wave of the same value, then you do not need to feed anything at the input. Okay. And this sine wave will be sustained in the system on its own. You can ask a question that, okay, if I do not feed anything, where will the sine wave arise in first place? Well, if this system is a model of some circuit block, there is going to be noise in the system. Noise exists at all the frequencies. Okay. At one particular frequency, which is omega naught, you will satisfy this criterion for sustained oscillations. And once you satisfy the criterion for one particular frequency, those oscillations will be sustained, all other frequencies input frequencies will die down. Okay. So, this is how our oscillator will be designed, right, so that it becomes self sustainable, right. Okay. So, using this this particular kind of negative feedback analysis, we will now go ahead and analyze one particular example. Okay. So, the example which I am going to choose is based on this loop gain and the angle loop gain only and Barkhausen criterion. So, let us do that. A simple example of a ring oscillator. Why we call it a ring, you will see. So, I have a simple common source amplifier, okay, designed with the help of a MOSFET R and C component. So, this is R and this is C. Okay. This, the gain, if I call this as V1, the gain from V1 to V2 for the amplifier at a given operating point can be found out. So, let us say you have this common source amplifier and it is biased at with DC voltages. So, we can find the gain from input to the output using the small signal model for this amplifier, and a small signal model for this amplifier, assuming that it is biased in saturation region, I can very well say this is V1, this is GM times V1, and you have resistor R in parallel with the RDS of the transistor, okay, and whatever capacitor we have, that capacitor I am going to have at the output. Assume that that capacitor is effectively CL. So, this is the model. So, V2 by V1 is simply minus GM times RL divided by 1 plus SCL RL. What is RL? RL is your R parallel RDS. Okay. So, this is the transfer function which you have, and this can be written as some DC gain A naught divided by 1 plus S by omega p, where A naught is equal to GM times RL and omega p is 1 over RL CL. Okay. So, I have this single stage here. The gain which you are seeing is you are having minus 180 degree and one particular pole. If I go ahead and cascade these blocks, for example, okay, like this. So, now I am going to connect all of them and form a ring like this. Okay. And let us treat this V1, this is V1, V2 and V3. So, from V1, V2 and from V1 to V2, V2 to V3 and back to V1, it forms one single system like this. Okay. This is the block which we have. For this particular block, if you think about it, we are connecting the output of the last stage back to the first stage. Okay. So, I am going to model this using our small signal model. So, the gain from the very first stage to the last stage is minus A naught by 1 plus s pi omega p into minus A naught by 1 plus s pi omega p into minus A naught by 1 plus s pi omega p. Okay. That is the gain for each stage, and the output finally is fed back here like this, and it is directly connected. There is no negative sign connected from the output of the last stage to the first stage. So, it is still in a positive sign. So, we have to take this into account, and there is no input to the system. Okay. Now, for this particular system, let me just draw it little nicely, okay, like this, right. We could have picked up at any particular point, but this is what we are looking at. So, here the loop gain of this system is minus A naught cube divided by 1 plus s by omega p whole cube. This system, as per the Barkhausen's criterion, it will become self-sustainable at above system becomes self-sustainable at omega equal to omega oscillation. Let me write it. If modulus of loop gain at j omega oscillation is equal to 1 and angle of loop gain at j omega oscillation is equal to 2 k pi. Now, you would ask that why did I write here 2 k pi, whereas it was 180 degree. Well, it was when it was 180 degree here, that time you had a minus sign here. So, 180 degree and this minus sign was giving you 360 degree. Here I do not have the minus sign, it is connected straight. So, I am writing 2 k pi, which is either 0 degree or 360 or minus 360 degree or so on. Okay. So, that is what we have. So, in order to do that, I will see whether I can have the frequency of oscillation or not. So, first I will write the angle of loop gain at j omega oscillation if this frequency exists. So, you look at the loop gain. So, for the loop gain you get 180 degree here, then minus 3 times tan inverse of omega oscillations divided by omega p. And as per our Barkhausen criterion for oscillations, if and only if this is equal to 2 k pi, then this is going to be k goes from 0 to infinity, it can take any value, then you will see that this is going to have oscillation. So, I will pick up k equal to 0, which implies that 3 tan inverse of omega oscillations by omega p is equal to 0. So, omega oscillation is equal to omega p times 10 of 60 degree, which is omega oscillation is root 3 times omega p. So, at the frequency root 3 times omega p, it happens that the phase of the signal is 2k pi. Now, this is not the only condition. The other condition is that the loop gain should also be equal to 1. So, I have to find this. So, this implies that A naught cube divided by under root of 1 plus omega oscillation by omega p whole square times cube, this is equal to 1, which is A naught cube is equal to I will put the value of root 3. So, square root of 1 plus 3 whole cube, this implies that A naught is equal to 2. So, if A naught happens to be 2 and then you have A naught happens to be 2 and omega oscillation happens to be root 3 times omega p, then you can get sustained oscillations for this particular example. Okay. And all the oscillators which are working on this negative feedback system, they are working on this principle only. Okay. Here you have seen a common source amplifier, you can have any other amplifier, you can cascade, and if you have the phase and the magnitude like this, you will see sustained oscillations. Okay. Now, it is not only this open loop system or this loop gain system which you have understood that you will have the sustained oscillations, it is also important to look at the closed loop systems, okay, for this example. So, given this example, right, what do you have here? This is, let us say, V in and V out. So, what we are going to look at is that if you have such kind of system, where do the poles lie of this closed loop? Poles of this closed loop, because when we make any closed loop system, it is stable if and only if all the poles are in the left half S plane. If you have poles on the right half S plane, the system is going to be unstable. Okay. So, what happens in the case of oscillator, whether the poles are in the left half plane or right half plane or j omega axis, we will confirm that. So, here if you look at the closed loop system, we need to find the poles or the roots of, okay, let me write it this, poles of above closed loop system will be given by the denominator of S, or 1 plus loop gain of S equal to 0, right, that will be the poles. So, to find the poles here, 1 plus loop gain of S, that is 1 minus or 1 plus minus 1 whole cube. So, look at this particular example here. So, what is the loop gain here? Loop gain is this, okay, and you are closing the loop in this particular manner, right. So, 1 plus loop gain is minus 1 cube into A naught cube divided by 1 plus S by omega p whole cube is equal to 0. Okay. So, here we find the poles of this loop, closed loop. One important thing here is that in this particular case, you are actually closing the loop with a positive sign. So, to give you an idea, let us just look at this system in general. When you have A of s, and here you use beta, or this is positive and this is negative. In this particular case, what you see is the following: A of s and beta of s in this case, right. So, this is x and this is y. Y by x is equal to A of s divided by 1 plus A of s beta of s. Okay. If it happens, you can rewrite those equations. If in place of this negative sign, you have a positive sign here, then y of x by y by x is equal to A of s divided by 1 minus A of s times beta of s. Okay. So, looking at our oscillator the way we are combining, it is going to be here 1 minus 1 cube times A naught cube. Okay. We need to find the poles for this. So, what we will get here is that 1 plus s by omega p whole cube is equal to A naught minus 1 minus A naught cube. Minus 1 cube is minus 1. I am just taking on both the sides, right. So, you have minus A naught cube. Okay. When you have this as minus A naught cube, you can write this as minus 1 and A naught cube. You need to find the closed loop poles. So, for the closed loop poles, you have to take the cube root on both the sides. So, 1 plus s by omega p is minus 1 divided by 1 over 3 times A naught. Now, taking cube root of minus 1 is can be done with the help of complex numbers. So, I can write s by omega p as minus 1 plus minus 1 power 1 over 3 times A naught. So, this minus 1 for whom I have to take the cube root is e power j 2 k plus 1 pi. Okay, this is the complex number representing minus 1, because e power j k pi, j 2 k plus 1 pi is equal to cosine of 2 k plus 1 pi and sine of 2 k plus 1 pi. Cosine is going to give you minus 1. This divide by 3 times A naught, and this becomes equal to e power j 2 k plus 1 pi by 3 times A naught. Here for the roots, k equal to 0, 1 and 2. Okay. So, the what roots we are going to have? Let me just write it at S0 is equal to omega p times minus 1. I will substitute k equal to 0. This is e power j pi by 3 times A naught, right. S1 is equal to omega p into minus 1. I substitute k equal to 1, k equal to 2 plus 1 3. So, 3 pi by 3, which is e power j pi times A naught, and S2 the third pole is minus 1 plus e power j, substitute k equal to 2, which is 4 plus 1 5 pi by 3 times A naught. Okay. And this value is nothing but it is minus 1. You can say 5 pi by 3 is like 6 pi minus pi by 3. So, this is e power minus j pi by 3 A naught. Okay. So, I will just expand this omega p times minus 1 plus A naught times cosine of pi by 3 is half, sine of pi by 3 is j root 3 by 2. This one e power j pi is minus 1. So, this is omega p into minus 1 minus A naught, and this value is going to be omega p into minus 1 plus A naught times half, this is minus pi by 3. So, half minus j root 3 by 2. So, the 3 poles which you are seeing in the closed loop which you will get, the 3 poles are equal to omega p or minus 1 minus a naught omega p. So, this pole is going to be in the left half plane. The other poles are omega p into minus 1 plus a naught half plus minus j root 3 by 2. Okay. So, for our sustained oscillations in this case, we found couple of things, that a naught is equal to 2. Okay. If a naught is equal to 2, then the roots of this closed loop system is minus 3 times omega p, okay, and the other one is minus 1 plus 2 times half plus minus j root 3 by 2. So, minus 1 plus 2 into half, this goes away, sorry, this part and this part cancel out. So, what you have is your roots are minus 3 omega p times plus minus j root 3 omega p. These are the other two poles. So, if you look at it, the location of the poles are like you have one at minus 3 omega p and the other two poles are on j omega axis. This is real of s, this is imaginary of s. So, now you can understand that if I choose a naught equal to 2, then at frequency root 3 times omega p, what happens is you have poles in the on the j omega axis, and which will give you sustained oscillations. Okay. So, what happens, what we analyze with the help of the loop gain and the phase, the same thing is revealed by the closed loop analysis, by the closed loop poles. If you have closed loop poles along the j omega axis, then you will have sustained oscillations. Okay. Now, if I take this system and this particular closed loop system, and I look at, I disturb the system which we have, and I just observe in transient domain. In case your a naught happens to be less than 2, case 1 is a naught less than 2, what you are going to see, there may be oscillations, but those oscillations will die down at V out. Okay. If you take case 2, where a naught is greater than 2, what you are going to see, for the closed loop system, you can very well get it from here. If a naught is greater than 2, then in that particular case, you are going to have poles, closed loop poles in the right half plane. The oscillations will build up, okay, and then with the with the real limit of the supply voltages, it may saturate either to VDD or ground. And in case 3, when a naught is equal to 2, in that particular case, you will get sustained oscillations. Whatever amplitude, we are not talking about that, but the oscillations are going to be sustained. In all these cases, I am plotting V out versus T. So, you can say it is important at some time that you have a naught greater than 2, so that the oscillations can start, but in sustained case there should be only a naught equal to 2 to have sustained oscillations. Okay. This analysis which we have done here using a closed loop system and the loop gain is form the basis of all kinds of oscillations which we can analyze using their small signal model. Okay. No matter which circuit comes up, having 3 in cascade, 5 in cascade, the way we have done in the ring 5, 7, whatever it is, we can calculate the frequency of oscillation and the gain required in this manner. Okay. Thank you.